Hello, geometers. Today we're going to talk about two-way tables or extend on what we had about two-way tables and a little more independence. So one of the difficult portions of two-way tables is sometimes putting in our information. So we have a situation here where I was conducting a survey of 200 total students. Now, a lot of times we saw this table yesterday with just car, no car, chores, and no chores. But today what I want you to do is kind of modify your two-way table and extend these lines because what we're going to use is rows and column sums. So the information they gave us is that the senior class students found that 78 students had access to a car. Now I know nothing about if they have chores or not. So that's where it's going to be a column sum, that I have 78 students that have a car. So fill this in with me that we have 54 students have regular chores, which would be a row sum. Now, the last piece of information they gave me was that 80 students neither had access to a car nor had regular chores to do. So that's a no and a no. In this case, no, 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 no. So we have 80 people that don't have a car and don't have chores. What I want you to do here is pause to see if you can fill in the rest of the chart. Again, the total number of students has to be 200. So if I add up this column, it should add to 200. This row should add to 200. This column, this row, whatever it may be, see if you can fill that in, and I'll do that quickly as well. So as you can see, I can add these up to have the 54 plus the 146 equal 200. So I know then 146 don't have chores. Well, if that's the case, to add to the 80, I need 66 that have a car and no chores. I can then find 12, I can find 42. Now, once we have the table, we can do some of the problems that we had yesterday. Let's make one up real quick about independence. So let's see if there's independence or an association with the probability of a car compared to if they have chores. Maybe if they have a car, they are doing their chores, or vice versa. Maybe there's an association, or maybe they're independent of each other. So in this case, what I need to do then is, given that it's chores, I'm going to highlight the chores row. And then I just zero in. I only look at that row and then see the probability of A. Well, the probability of A is, do they have a car? So I'm just going to look in this row. That's 12 people out of 54. Compared to if I just say, probability that they have a car. Maybe they have chores, maybe they don't. But the probability that they have a car is 78 people have a car out of 200 total. So let's see if these two are equal to each other. In this case, the decimal for 12/54 was 2/11 or 0.222, and then 0.39 for our other side here. So these are not independent. So there may be an association between having a car and having chores. Even in this point of the video, I would highly, highly, highly suggest pausing and seeing if you can fill in this table. If you can't fill in this table with the information that's given up above and the more information that they give, everything after this is going to be very, very difficult if you just wait for me to do it. So why don't you take a second, read the problem, see if you can fill in this chart, and then I'll give you a little bit of help. So this is the information that was given in the situation. Then you need to fill in the row and column sums. Now that we have the added values, we want to start going with the actual probability questions. So in part B here, it says if Mr. Cooper randomly selects a student, what's the probability he selects a boy who previously took the folder? Now, they want us to make a new two-way table and fill in those probabilities, just so we have them as actual probabilities, and then fill in the remaining cells with the respective probabilities, including row and column totals. So as you can see, just divided by 30 finds the probability of each cell. And in part B, it says, what's the probability he selects a boy who previously took the folder? So it's, since a given boy, that we have a 4 out of 30 chance of getting that. In part C, it asks if a student is chosen at random, so we're not any givens, it's just the whole table. What is the probability that a student is a girl or is a student that has taken the folder previously. So we're going back to our probability rules that if I have the probability of A or B, remember that's the probability of A plus the probability of B, but then I'm going to subtract any overlap. Or really you could just grab the ones or the probabilities that fit this or. So in this case, the probability that they are a girl is 12 out of 30. The probability that it had previously taken the folder is 7 out of 30, but then I have to subtract any overlap, meaning in this row, in this column and this row, the overlap is right here. And if I kind of circle this one, circle that one, I have to subtract 3 out of the 30. So my total probability then is 19 minus 6, which is 16 out of 30. We'll skip part D for now and get to more two-way tables. So in 10-92 is another situation where I would highly suggest stopping the video, take your time, see if you can fill in the two-way table. We have exercising and eating 5 servings of fruit. Try that out, pause. So again, we need to be careful of the given information. I've put the given information here if you struggled with that. Notice that these are totals. So that 35% is just total. I don't know about their eating habits. They just checked that they exercise regularly. So again, we have some overlaps, but we got to take care of that in our two-way table. So if you didn't get that before, again, I would pause. See if you can fill in the rest of this table. Now that we have the table filled in, now we can ask you all those probabilities and conditional probabilities and independence and mutually exclusive questions. So let's go through the ones they have for here. In part B, what's the probability that a freshman in the study exercises regularly and eats 5 servings of fruits and vegetables each day? That's my overlap. That's my yes, yes. In this case, exercises and has 5 servings a day. There's a 25% chance of that happening. What's the probability that a freshman in the study exercises regularly or eats 5 servings of fruits and vegetables each day? Let's set up our probability of A or B. So just to show our overlap this time, I've highlighted the row of exercise, which is yellow. So the probability of exercise regular is 35% chance of that happening. The green column is plus my probability of B, 33%, and then I just have to subtract the overlap. The overlap in this case is 25%, which I believe that is equal to 43% chance of that happening. Now it says, do you think the freshman who eats 5 servings of fruit and vegetables per day are more likely to exercise? In other words, are exercising and eating associated? So all we have to do to check for association is check if they're independent. Does exercising really affect your ability or the chance that you eat vegetables 5 servings a day? And I'd like to highlight in part D as well the order that they asked of this. It says, do you think that freshmen who eat 5 servings of fruits and vegetables per day are doing something? That means given that they are eating 5 servings a day, does that change the probability or are they more likely to exercise? So notice my order here is given they have 5 servings, are they more likely to exercise? So we're saying what's probably of E given 5 servings. So I'm going to have my given 5 servings, which is this column here. And then just highlight their conditional probability. Just look in the red. What's the probability of E? That's 25 out of this column, 25 out of 33. Now these are percentages, but I can divide the decimals as well, and it will get the same relative decimal from that. And then the probability of exercising is 35% out of the 100. So I can just take 35 out of the 100. Let's check to see if these are the same, but I think you can kind of tell with them. So as we've compared these decimals, you know, a much higher probability of E given 5 servings. So these are not independent. They're not independent, meaning they have an association. Probably if you eat 5 servings a day, you're caring about your body, and there may be association of how much you exercise. So association or associated, not independence. All right, let's talk a little bit more about that independence. So we're going to go back to a problem in 10-93 about this game, the spinner game, when we were finding expected value. But actually, let's see if we can represent that on a two-way table and introduce the idea of a multiplication rule. So for the double spin game, I made it as two spinners, but remember, to win, you have to get the same spot. Essentially, you have to get 100 and 100 if you're going to win. You're going to have to get 10 and 10 if you're going to have to win. So in part A, we did that before, so I just wrote it on the bottom here. It says, make an area model to show the sample space of every possible outcome for two spins. What's the probability that Nick wins? So in this case, to win, all you really have to look at is the diagonal. So what I can do is add up those probabilities, and that's the probability that he just wins some money. Now in this case, when Nick came home from the fair, he told Zach, hey, I won some money, but he didn't say how much. In this case, it says, knowing that Nick won some money, what are the chances that he won $100? Well, that's a given situation. That's conditional probability. Given that he won some money, which I can find in this diagonal, it's really picking the spot that he can, which would look like this. So conditional probability, we're going to circle what our condition is. The diagonals where he won. They'll get $100. It would be 1 out of 64. So 1 out of 64 divided by the 18 out of 64 chance of winning, which we got in part A. Dividing fraction, just flip and multiply. So the 64 is reduced. The probability that he actually won the 100 is 1 out of 18, given that he actually won some money. So this would be another great opportunity to pause the video. It says make a two-way table that shows the probabilities for the double spin game. How does your table compare to the area model for part A? So think about how we can put the information for the situation into an area model. Try that probably before you move on. The fact of the matter in part C is that the two-way table compared to the area model are going to look pretty much identical, exactly the same. Now, I'm not going to fill that in, but it may not look like this. You could make a specific two-way table, like if you went money, no money, and then if we're talking about the $100 situation, but really, the table to the left here, that is the two-way table. The row sums and the column sums are already there. This row has to add, column has to add up to 1/8. This one has to add up to 1/8. But how does that help us with talking about independence in this sense? So we're going to switch our focus to the multiplication rule. So the multiplication rule, or mathematical way to express conditional probability, is kind of what we're doing with the circles here. It says the probability of A given B. Well, the probability of A given B is the probability of A and B. That's the red. So red divided by green. But you notice that we can maybe start rearranging this. Now that we have some information that we know about given and independence, we're going to talk about the relationship called the multiplication rule. So this is one version of our multiplication rule. But using what we have for independence, we can actually write a different format. So if there is independence, then we said the probability of A given B would equal the probability of A. So by using this, we assume that if this is true, there is independence. So what I can actually do is substitute what I know for the probability of A given B. Probability of A given B then could be the probability of A, and that would equal then the probability of A and B over the probability of B. I just substituted this essentially as the probability of A. Doing a little algebra, doing a little rearrangement, I could check for independence then by multiplying both sides by the probability of B. And this is why we call this the multiplication rule. I'm going to rearrange it a little bit to put the probability of A and B, or if the probability of A and B is equal to the probability of A times the probability of B, you have independence. So certain situations, these might be way easier to find. They just give you the probability of something happening, probably a second thing happening, and then they have the overlap. If those two probabilities are equal, they have independence. So again, we have different variations of the multiplication rule. And this format here. We have this format here. But now with certain situations, we can test this to see if there's independence. So now let's look at the two ways we can show independence and association. Why don't you pause the video and read through the scenario here and see what this would look like in our two-way table. So as you can see, I've put in the given information from the scenario, but it might take me some time to fill in the rest of this table. So let's look at our other version of the multiplication rule and we'll compare it to this original. Really then I'm looking for the probability of A and B and see if that's equal to the probability of A times the probability of B. Let's find those from our chart. This time in this scenario, I have the probability of A and B right there. It's just sitting right in front of me. That's 72 out of 240. The probability of A, in this case, would be a washer. I have 180 over 240 times the probability of a dryer, which is 96 over 240. Let's get these to their decimal form. And as we can see from our calculator, we do get the same decimal on both sides. So there is independence, meaning buying a washer doesn't really affect if you're going to buy a dryer or not, or I should say buying a dryer doesn't affect if you're going to buy a washer or not. It might, might think there's association, but the numbers aren't holding up. It may be just replacing one thing for another. Not that people are going to buy a set. There's lots of explanations from that. But from the laundry shop here, the data shows that these two ideas were washers and dryers, and when we buy them is independent. So hopefully this helps. We have two ways now of finding independence. If you want to try it, you could fill in the rest of the table here and do the probability of wash and give or dryer and see if that's equal to the probability of washer. Hopefully you see that those two are equal, but with given information or certain given information, it may be easier just to use this version of the multiplication rule. Hope this helps. Happy probability finding.